Here in video 21 of Tensor Calculus, we'll pick up where we left off last time and continue to look at algebraic operations with tensors. In particular, we'll focus on an operation known as contraction. In the last video, we introduced the concept of an outer product or a tensor product. And just as a quick reminder of what that is, we're multiplying two tensors together. Here we've got a second-ranked tensor times a third-ranked tensor, and it produces a fifth-ranked tensor. Well, today we're going to take a look at something that looks very similar, but it is distinctly different in its meaning. All right, there are two important differences here. First of all, these two indexes represent a pair of dummy indexes. Up here, J and R are both free indexes, but here we've got a dummy index pair. And the other thing is that here we've got 5 free indexes. Here we've only got 3 free indexes. Well, we call this kind of thing an inner product or a contraction. This is an outer product. It's got 5 free indexes. They're all unique, and there are no dummy indexes. And you'll recall that means that we have actually 3 to the 5th power, or 243, different relationships expressed by this one equation. Now this is an inner product. It has a total of 3 free indexes and 1 dummy index. That means that this represents 3 to the 3rd power, or 27 different expressions simultaneously. However, the dummy index implies a summation, which means the left side of this expression contains 3 terms. Now the claim here is that this inner product will produce a third-ranked tensor. So let me show you how we prove that. First of all, I'll re-express the product with a delta factor. Now notice what I've done. I've changed the J index here to R, and I've added this delta factor out here. Now normally when you'd see a product like this, you'd say that the R index would be absorbed by the delta factor, leaving a J here. And we would replace this with this. But it works both ways. If this equals this, then we can go the other way too. Now the reason I'm doing that is so that the indexes in P are unique from those in Q. And what that lets us do is to replace each of these factors with the corresponding expressions needed to transform from the prime coordinate system. So it's like this. You've seen this many times. This pair of Jacobian factors along with this will transform to the unprimed system. These Jacobian factors with this factor will transform back to here. So I'm just replacing each of these with their equivalent in terms of the prime coordinate system. Okay, well now we simply rearrange the terms. All I've done here is just to reorder terms, and what I've done, I've taken this factor over here and this factor over here. Now why would I do that? Well, I do that because this J index is a dummy index with this J index, and R is a dummy index here. And that means that this expression is what we'd use to transform to the prime system. In other words, this product right here is the same as this. This transforms from the unprimed system to the prime system. Well, now we have a dummy index here, so this delta J prime R prime factor will absorb the R prime index, leaving us with this expression. And that proves that the product that we're talking about here transforms from the primed coordinate system to the unprimed coordinate system using these Jacobian factors. And these are the 3 factors that would be needed to transform a third-ranked tensor. Well, now we can simply replace this with its equal here, and this one with its corresponding counterpart. So that gives us the proof we need. R is a third-ranked tensor. It transforms from the prime coordinate system to the unprimed coordinate system using these 3 Jacobian factors. Now the important takeaway here is that the transformation involves only the free indexes. you'll notice that the Jacobian factors only relate to indexes I, S, and K. And that means in turn that the rank of the expression is determined strictly by the free indexes. The dummy indexes do not participate in the transformation nor the establishment of the rank of the expression. Now I'm sure you can see how this generalizes. If we had a second dummy index here, say the first and the bottom one here, what we'd wind up with was be an additional delta factor here, and that in turn would result in another term like this out here. The second delta factor would absorb, in effect, two of these Jacobian factors, and in the end there'd be only one Jacobian factor left when we got to the bottom line down here. So a second dummy index would reduce the rank again by two more, leaving us with only a first rank expression. So another way to look at this is that we can establish the rank by looking at the total number of indexes in our product and subtract 2 for each pair of dummy indexes that we find in the expression. And that'll give us the proper rank of the output. Again, the rank of the output of a inner product is always determined strictly by the free indexes and not by the dummy indexes. Now, why do we call it a contraction? Well, look at this. Suppose we had a second rank tensor, Tij, and we multiplied that by Sk. This, of course, would be an outer product. Well, here we started with a second rank tensor multiplied by a first rank tensor, and this is going to give us a tensor of rank 3 as an output. But if we start with Tij and multiply by Si, we're forming an inner product. And this time what we're producing is a tensor of rank 1. So we started with rank 2 and generated a third rank tensor this way. Here we started with a second rank tensor and generated a first rank tensor. We have in effect contracted the second rank tensor into a first rank tensor by multiplying by this kind of a factor. So that'll give you just a little insight as to why we call it a contraction. Alright, let's move on and look at another type of contraction. Here we're dealing with just a single fifth rank tensor. There is no product at all. What we've done is to set two of the indexes equal to each other. We've duplicated one of the upper indexes with one of the lower indexes, and this is a form of contraction. Now at first glance you'd wonder if this even makes any sense syntax-wise. Well, let's remind ourselves of what it means. The J index is an implied summation, so this is really Qi1s 1k plus Qi2s 2k plus Qi3s 3k, and we say that that's equal to Risk. So it does make sense syntax-wise. We're just adding three terms together in each case to get the corresponding element of Risk. So it boils down to this. If we know that Qijs mk is a fifth rank tensor, then if we form a contraction by setting the J index equal to the M index like this, Ijs jk, will this produce a third rank tensor? This is a fifth rank tensor, and what we did was to equate these two indexes, and the claim is that that will produce a third rank tensor. Well, let's see if that works. The proof works just like it did for the inner product. We start by adding a delta factor, so we've changed J to R here and added this delta factor. And then that lets us replace this factor with its equivalent in the prime coordinate system, so it looks like this. These Jacobian factors combined with this factor are the same as this. Now we're going to rearrange the Jacobian factors. We take two of them to pair up with the delta factor here because that's what we'd use to transform to the prime coordinate system. So it now looks like this. This transforms to this. And now the R prime index is absorbed, giving us this result. showing that this expression transforms to this one using 3 Jacobian factors. And now we can replace this with its equivalent and the other side with its corresponding value of r, I prime, s prime, k prime. And that proves that the output is a third-rank tensor because it only uses those Jacobian factors that relate to the free indexes of the expression. So everything we said about the contraction for an inner product is relevant here as well. Now, you might be wondering, how did I know to contract the second upper index with the first one on the bottom? Well, I did that because I could. It'll work in any case. For example, QIJS, contracting it this way, contracting the second index with the second one on the bottom, that also works. It gives us a different tensor than this contraction, but it is also a third-rank tensor. So we can contract any upper index with any lower index and be guaranteed that the output will be a tensor, and the rank of the output will always be 2 less than the one we started with. Okay, let's move on. We began the video by introducing the inner product, and that's of course what we have here. We said that if P is a tensor and Q is a tensor, then R is going to be a tensor. Well, it turns out that the converse is true. That is to say, if R is a tensor and P is a known tensor not equal to 0, then Q is a tensor as well. And the proof is really pretty simple. What we'll do is to multiply both sides of the expression by a couple of arbitrary vectors. And the vectors are chosen so that they form inner products with indexes s and k. So on the left-hand side, we have a full contraction. There are no free indexes. They're all dummy indexes. Now, if you go back to video number 19, you'll remember that's one of the definitions of a tensor. A tensor is a system of objects that's indexed like this, such that if it's contracted with arbitrary vectors, it will form a scalar function. So this is a scalar value. It's independent. It's an invariant. Because we know that R is a tensor, then this expression is a scalar function. Well, that means that this side is a scalar function too. And over here we have the same concept. We have an index system that is contracted with 3 arbitrary vectors. We've got contraction with S, one with K, and one with J. So because this system contracts with arbitrary vectors to form a scalar function, then we know that Q is a tensor. It's as simple as that. Now, I'm not going to prove it here, but it turns out this relationship is true in a more general sense. For example, if we know that this is a third-rank tensor and this is a second-rank tensor that is not 0, then that'll tell us that Q is a tensor as well. So the general relationship is this. If we have a known tensor that is the product of 2 other terms like this, whatever rank and relationship, such that one of the 2 factors is a tensor, then the other factor will be a tensor too. Now, this is a very important result that's known as the quotient theorem. The quotient theorem gives us an additional method to determine if something is a tensor, and you'll see it come into play quite often. Let me give you a quick example. Back in video number 17, we defined the contravariant metric tensor. We said that that's equal to Zij contracted with Zjk in such a way that the result is delta Ik. Well, we said that this factor is a tensor, but we never really proved it. So we can do that now very easily with the quotient theorem. We know that the Kronecker delta is a tensor. We know that the covariant metric tensor is a tensor. Well, that tells us this is a tensor. We have a tensor that's equal to a product of 2 other expressions, one of which is a known tensor that's not equal to 0. So that's all the proof you need to prove that Zij here is in fact a tensor. And of course, the index structure tells you that we're correct in establishing it as a contravariant object. Okay, let's move on to one final topic. For the last couple of videos, we've been looking at operations with tensors. We now see that we can equate them, add or subtract them, multiply them by scalar values, and even multiply them together to form outer or inner products. What's becoming apparent is that working with tensors is very much like working with simple algebraic expressions. Well, that leads naturally to the question of division. Is the operation of division valid with tensors? Well, certainly the operation of dividing by a scalar value is okay. I mean, that's just a matter of multiplying by the reciprocal. So we've got that covered just by multiplying by fractions. But what about an expression like Tij divided by Skm? Would we ever see anything like that? And the answer is no. This sort of expression makes absolutely no sense whatsoever, so you'll never see a division of this sort in tensor equations. Well, that having been said, let's consider the expression you see here. You know, in algebra, if we had an expression AB equals to 0, we'd know that we could cancel out B and set A equal to 0 as long as we knew that B itself is not equal to 0. Well, when we say we're canceling out the factor of b, what we're really doing is dividing both sides of this expression by b to get this result. And we know we can only do that, of course, if b is not equal to 0. Well, another way to look at it is to say that we are multiplying both sides of the expression by the reciprocal of b. We're multiplying both sides by 1 over b, and when we do that, this product is 1, and 1 times a is simply the result that we have here. Well, it turns out we can do something very similar up here. Although we cannot divide by Qj, we can multiply both sides by a reciprocal. So let's see how that works. What we're going to do is to multiply both sides of this expression by an arbitrary vector. We're going to multiply by aj, with j being the upper position. A is non-zero and it's an arbitrary vector. And as long as we know that Qj here is not equal to 0, then this product, this contraction, will form a scalar value. All right, and that scalar value will not be equal to 0 because we know that Qj is not 0, nor is A. So this is a non-zero scalar value, and therefore it has a reciprocal. We can now multiply both sides of the expression by the reciprocal of this value, and that will lead us to the fact that Ti is equal to 0. We are able, in effect, to cancel the factor of Qj out, leaving us with Ti equals to 0. Now, this canceling operation, again, is not division. It's a multiplication of a reciprocal value. And although we can't divide in tensor calculus, we can certainly multiply by reciprocals. Now take a look at this expression. What we'll do here is to subtract Si Qj from both sides and factor out Qj. So we would have Ti minus Si times Qj is equal to 0. And using the same logic we used up here, we can eliminate this factor, and that means that Ti minus Si is equal to 0, or Ti is equal to Si. The end result is that we have in effect canceled these common factors out of this expression to get this result. Now this is something that can always be done with an outer product. As long as we know that the common factor is not equal to 0, then we can cancel out the common factors and get the result like this. It always works with any outer product. Well, let's see if the same thing works for inner products. Okay, this time we have an inner product. I here is a dummy index. So let's try our technique. We're going to try to eliminate Qi by forming a contraction using an arbitrary vector. But this time we run into a snag. Qi is already part of an inner product, so I can't form a contraction using an arbitrary vector. I can't use I in this position because it's already in use as a dummy index. Therefore, this technique does not work. we cannot conclude from this process that Ti is equal to 0. It may be, but we simply can't prove it using this technique. The fact is that unlike simple algebra, it's possible to form a product of 0 even though neither of the two factors is equal to 0. Now let me illustrate that point with a specific example. What I've done here is assign the components of Ti and Qi respectively. Let's form the inner product here. Well, the inner product is T1 times Q1 plus T2 times Q2 plus T3 times Q3, and the sum of all that is equal to 0. So the inner product of these two vectors is equal to 0, and neither of these two vectors is equal to 0. Therefore, we cannot conclude that just because Qi is not equal to 0, that we can cancel Qi out and set Ti equal to 0. We cannot conclude that Ti is equal to 0 just because Qi is not. However, there is a condition that will allow us to cancel Qi. We can conclude that Ti is equal to 0 provided we know that Qi is arbitrary. So what we're saying is this: suppose we have a relationship like this and we know it's true for an arbitrary value of Qi. Well, by arbitrary, we mean any possible choice. Down here, our example depended on using a specific choice of Q to make the inner product equal to 0. If we had chosen any other value for Qi, then the inner product would not have been 0. But if we know we have a situation where the product is going to be 0 no matter what we choose for Q here, the only way that inner product can be 0 is if all of these components are 0. So that's why we can make this conclusion. Ti will be 0 when Qi is arbitrary. And that's what allows us to cancel this factor out. Okay, well let's summarize then. What we've discovered is that we can cancel out common factors of any expression of an outer product just as long as we know that common factor is not equal to 0. But we can only cancel out common factors of an inner product if we know that that inner product factor is arbitrary. Okay, with that, let's wind things down with a review. What we did in this video was to introduce the concept of an inner product or a contraction. An inner product is very much like an outer product, except it has one or more dummy indexes. Now in either case, we're going to multiply two tensors together to get a tensor. If P is a tensor and Q is a tensor, then R is going to be a tensor as well. The difference is that with an outer product, we would have produced a tensor of rank 5, while here we're producing a tensor of rank 3. So the principle is this. To determine the rank of the expression, we look only at the number of free indexes, in this case I, S, and K. As an alternate method, you could look at the total number of indexes over here and subtract 2 for each dummy index. Next, we showed that something similar happens when we form a contraction using an individual tensor. Here we've renamed the indexes so that J is now a dummy index. We can do this with any upper index and any lower index. And when we do it, we'll produce a tensor whose rank is 2 less than the one we started with. In this case, we started with a 5th rank tensor, and the single contraction forms a 3rd rank tensor like this. So the rules for determining the rank of the expression are the same as with a product. We look strictly at the number of free indexes, in this case 3. Or we can look at the total number of indexes here and subtract 2 for each dummy index. Next, we introduce the quotient theorem. Here, if we start with 2 known tensors and multiply them together, we know we'll get a tensor. Well, the quotient theorem is just the converse of that. If we start with a known product that is a tensor, and we know that one of the factors is a tensor that is not equal to 0, then we can conclude that the remaining factor is a tensor as well. This is a very important result that gives us an additional way to determine if something's a tensor, and we make frequent use of it in future videos. And finally, we showed that under the right conditions, it's possible to cancel out common factors. Now, for an outer product, all we have to know is that the common factor is not equal to 0. And if that's true, we can simply cancel them out like this. Now, although this looks like division, it's really not. Remember, we accomplished this by multiplying both sides by reciprocal values. Now, for an inner product, this test is not sufficient. In order to cancel out common factors there, we have to know that the common factor is an arbitrary factor. That means that this expression is going to be true for any arbitrary value we select for our common tensor. Now, if that is the case, we can cancel out common factors of an inner product just like we do for the outer product. Okay, well, in the next video, we're going to show how we use contraction to raise and lower indexes.